Welcome to the Intelligent Electrical Power Grid section. We work on the power system of the future. Why do we do that? Decarbonizing our society turns the power system upside down. We have to change a lot. New topologies, new controls, new markets, new protection, power electronics, lots of digital technology, algorithms, data, digital twins, cybersecurity, and so forth. We are around 50 scientists working on all that. Let me show you a bit of that.
Integration of renewables and power electronics in the power system of the future makes the system really complex. The power system becomes hybrid and it consists of an AC grid and high voltage DC links. We design algorithms for modeling, stabilizing and controlling of the hybrid power systems.
Electrical power grids can span entire continents and interact with other energy networks such as gas or heat networks. So how can we know what's going on in such a massive grid? And more importantly, how can we predict what might happen in the future and control this? So for this purpose, we work with data analysis to identify patterns. We work with machine learning to predict what might happen next. And we are developing control tools for the control room of the future.
Modern grid protection is crucial for the safety of future power systems, and it is inevitable to secure the power systems from large blackouts. Loss of every kilowatt-hour electricity causes financial loss for the utilities, companies, and it is incredibly important for our hospitals, especially in these difficult times.
We developed a technology that keeps the lights on, and we can even hack these intelligent electronic devices. A cyber attack on digital substations can lead to equipment damage, cascading failures, and even a blackout. Therefore, cybersecurity is an emerging topic to secure the power grid from hackers.
Future multi-energy systems have different physical properties. For example, time-varying inertia, short-circuit capacity, and network impedance. For such systems, we need supercomputers that can interact with real power hardware in real time. This enables testing the capabilities of any power electronic interface device. For instance, electrolyzers, wind power plants, or battery storage, to support the stability of the multi-energy system. Future multi-energy systems have different physical properties. For example, time-varying inertia, short-circuit capacity, and network impedance. For such systems, we need supercomputers that can interact with real power hardware in real time. This enables testing the capabilities of any power electronic interface device. For instance, electrolyzers, wind power plants, or battery storage, to support the stability of the multi-energy system. This is our RTDS supercomputer lab. In the black cubicle, we have two Nova Core chassis that allow us to model systems with up to 8,000 single-phase nodes. The cubicle is connected to a grid emulator. The grid emulator receives signals from RTDS to create real voltages and currents like those being simulated in the Nova Core. These signals are controlled and exchanged with a so-called device under test. The device under test is, for instance, a new controller that provides synthetic inertia. Let's see how this works in a multi-energy hub with hydrogen electrolyzers and wind turbines.
This research requires smart people, smart students. Luckily, there is an entire portfolio of courses and activities that will prepare you for that. Check our webpage and you'll find courses such as power system dynamics, transients, intelligent electrical power grids, and power systems of the future. They combine theoretical insight into these fascinating problems with practical experience, such as here at the RTDS supercomputer. We work closely with international peers and industry, and we try to involve our students as much as possible. If you want to create the next generation power system that is clean, fair, and resilient, get in touch with us. It happens here.